we can construct our classes again. Let me remember the definition of algebra. Okay, Sajja, thank you. We see this definition for Banach algebra with a algebra. The algebra norm on A is a as this from A to R such that A with this norm is a norm space. And further, we have this inequality for any A and B. The norm of AB is less than or equal the norm of A multiplied by the norm of B. Okay? Please note that this A is a algebra, so AB is an element of A. The multiplication AB is defined in our algebra. And the norm algebra A and this norm is a Banach algebra if this norm is complete. If we have this inequality and this norm is complete, then this is a Banach algebra. And we see some examples such as this and other examples at infinity. And finally we see this example. Let A and F be two linear spaces or vector spaces. Then L of E and F is the all linear maps from E to F. It is itself a linear space. This is a linear space. E and B linear spaces. This is a linear space too. For the standard operation, okay? And we see this example. Now let E and F are spaces. Then B of E and F is a family of all bounded linear operator or continuous linear operator from E to F. We know that continuity and boundedness are equal for linear maps. Okay? So that this is the set of all linear bounded functions from E to F or linear continuous functions from E to F. And B of E and F is a subspace of L of E and F. And this subset or subspace itself is a Banach space for the operator norm given by this equality. For any T in B of E and F, the norm of T or the operator norm of T equal to this supremum. We write L of E and E for L of E and E and B of E and E respectively. The product of two operators S and T in L given by composition of two, okay, S of T of each equal to S O T of E. This space with this multiplication is a we see this equality and the proof of that B of E with composition is a Banach algebra. Let okay. Let me open a board for operator theory. Okay. This is the last example of Banach algebras. This example. Below and L of E and F, the set of all T from E to F, that T is a linear map. Then L of E and F by the following ordinary operation is a linear space. Okay? Operations. Okay, operations, okay, is a linear space. These two operations, addition and scalar multiplication for any T and S in this space, T plus S is a function from E to F again by these function rules. So that T plus S is a function from E to F again. And for any T in L of E and F, and for any scalar alpha, alpha T of X equal to alpha multiplied by T of X. So that alpha T is a function from E to F. And it is very trivial that these two functions are linear. So that these two are elements in L of E and F. Trivially, T plus S and alpha T by the above definitions are linear maps from E to F. Now let E and F be Banach spaces. A linear map such as T from E to F is called bounded whenever there exists a real number such as M, such that we have this inequality for any X in E. The F norm of T of X is less than or equal M multiplied by the E norm of X. And the set of all bounded linear maps from E to F denoted by B of E and F. So that this is the subspace of L of E and F. Now we define a norm on this space. The operator norm equal to this. the supremum of this norm for any x in E with this property, or this, and this. All of these are equal. Okay? And this is the function norm on this space that is called the operator norm. That we see the properties of norm for this function norms. The norm of t is non-negative, t equal to 0 if and only if the norm of t equal to 0, and this equality, the norm of alpha t equal to absolute value of alpha multiplied by the norm of t. And finally, triangle inequality. We have triangle inequality. So that this is the norm. B and E are B of E and F with the operator norm is a norm space. Also, this is the we have this proposition: if E and F are norm space, and this is the operator norm on this space, then B of E and F with the operator norm is complete if and only if F is complete, the second space. Okay, so that this is the complete norm space or Banach space. Now we consider equal to F and denoted these two space by this abbreviation, so that L of E is a linear space and this is a Banach space and Banach subspace of this L of E. If we consider composition operation on B of E, then we see that for any S and T in this SOT is an element of B of E. And so this is a binary composition, is a binary operation on this space. Muhammad, do you have my voice? And we have this equality. This is very important for any x in E. The norm of t of x is less than or equal the norm of t multiplied by the norm of x. This is the operator norm. Okay, operator norm. So if S and T belong to B of E, then for any x in E we have this norm, or this norm is less than or equal the operator norm of S multiplied by the norm of T of X. And now this norm is less than or equal the operator norm of T multiplied by the norm of X. So that we have this inequality. We have this inequality. And this shows that SOT is bounded. So we have this implication for any S and T in B of E. SOT is an element of B of E. SOT is a linear bounded function from E to E. And also by a star we have this inequality. So the operator norm is an algebra norm on B of E. And the identity map is the unit of B of E. Finally, we have this proposition B of E, and the operator norm is a unital Banach algebra. This is the last example for Banach algebras. For example, let F be the finite dimensional space Cn. We know that any finite dimensional vector space on complex number isomorphic with C of n, say with the Euclidean norm, then L of E equal to B of E. In this space, if we consider E equal to this finite dimensional space, L of E equal to B of E. Any linear map is bounded or continuous, okay? And we know that this space equal to the space of all n times n matrix on with complex variable, okay, of n times n matrix over C with the usual identification. This is a particular case of curious example. Okay, let me write this for you. As an example, if we consider E equal to a finite dimensional space such as this, then L of E equal to B of E and equal to the set of all n times n matrix over C. So that this is a Banach algebra 2. And we can consider this example, the algebra C of X of formal power series in one variable consists of sequences such as alpha n, where alpha n's are complex numbers with coordinate-wise linear operation and the product by this equality. The multiplication of these two sequences is another sequence gamma n, for example, such that gamma n equal to this summation. It's helpful to think of elements of this space as formal series of this form, then we can see this multiplication, okay, with the product suggested by the symbols. This algebra contains as a subalgebra the algebra C of x of polynomial in one variable. This polynomial corresponds to the sequence alpha n that are eventually zero. Okay, eventually zero. It is not that any polynomial is in particular case of a power series. This power series for example f equal to this, okay, but or we can write a0 plus a1x plus a2 x2 and up to the end. But for an polynomial we have this form, okay, a0 plus a1x plus a2x2 up to the amxm. So that this is a particular case of a power series, because for any k greater than m, am equal to 0, okay, or ak equal to 0. And let me write this a instead of alpha because I write am, okay. And we have weight and L1. Let me write for you this example. Let's x, a and mu be a measure space. You know the definition of measure. Let me recall this for you. For example, in this definition, suppose X is a set and S is a sigma algebra on X. So that this is a subset of the power set of X. This S is a subset of the power set of X, such that contains empty set, and it is closed under complementation and countable union. This is a sigma algebra on X. A measure on this measurable space is a function such as mu from S to 0 up to the infinity, such that mu of empty set equal to 0, and for any disjunct sequence such as E1, E2 up to the n, in S we have this equality, mu of the union of Eka equal to this summation. Then we say that mu is a measure, and we say that x, S and mu, or A and mu, is a measure space. We consider our sigma algebra A, okay? Or we can consider this set L1 of X equal to the set of all F from X to C, such that F is a measurable, that you see the definition of this, and this integral be finite, okay? It is very trivial that L1 with the ordinary operation addition and scalar multiplication is a vector space, okay? L1 with the ordinary plus and scalar multiplication is a vector space. Is a vector space. For any T1 and T2 in L1 of X, T1 plus T2 of X equal to T1 of X plus T2 of X for any X in X, and also for any T in L1 and for any alpha in complex numbers, alpha T of X equal to alpha T of X, again for any X in X. These are two addition and multiplication operation in this space. It is very easy that these two functions are in L1, okay? And if we consider for any T and S, for example, in L1 of X, if we assume that and S are equal if and only if T equal to S mu almost everywhere, then this is a norm. We consider on the other hand, if we consider mu almost everywhere functions equal, okay, equal, then we have the following norm on L1 of X. This norm for any T in L1 of X or for any F for L1 of X it defines this norm, L1 norm. Okay, because we assume that this is a finite or real numbers. Okay, this is a real numbers. Okay, this is finite. It is trivial that this is a norm function. We have three properties for norms. One, for any F in L1, this is positive, and this equal to 0 if and only if F equal to 0 mu almost everywhere. Or by these assumptions, F equal to 0. F equal to 0 by this assumption. We consider mu almost everywhere equal functions equal. Mu almost everywhere equal functions equal. So that this is the identity element in our space. 2, for any F in L1 and for any alpha in complex numbers, we have this property that this is equal to this integral, okay? And we know that this is equal to the absolute value of alpha multiplied by this integral. but this is the norm of f, so that this is equal to this multiplication. And finally, for any f and g in L1 of x. Dear students, do you have my book? The norm of f plus g, norm 1, equal to this integral wa alaikum assalam, and this is less than or equal this integral plus the absolute value of f plus absolute value of g, okay, d mu is whole by triangle inequality in complex numbers, okay, and we know that this is equal to this integral plus this integral on x and x, and the first one equal to the norm of f and the second is the norm of g, so that we have triangle inequality in this space, and this is a known. Also we know that L1 proposition let x a mu be a measure space, then L1 with L1 norm is a Banach space, okay, this norm is complete. You can see the proof of this in all functional analysis books, very easy, that this norm is complete, okay. But we want a Banach algebra. For algebra we need a multiplication on L1. For this, now let x equal to or x be a group such as G, okay, we consider x equal to a group G, and define the convolution product as this equality for any f and g in L1 of g, okay, because we consider x equal to g. F a star g of x equal to the integral of f of y, g of y minus x, d mu of y on g for any x in g, so that we have a function f star g from g to c, and also we have this important equality that we need this for any f and g in L1 of g, f star g norm 1 is less than or equal this multiplied by this. Okay, if we prove this inequality, we see that this norm is a algebra norm on L1 of G. Please note that we consider X as a group because we need to the inverse of elements. Okay, y belong to G, so that y inverse is an element of G, and this multiplication belong to G because G is a group. Okay, finally this multiplication is a complex number function, and we can consider this integral. And for this we see that so let me write this. So norm 1 is a algebra norm on L1 of G. Okay, because the proof of this inequality for any f and g in L1 of G, we have the norm 1 of f star G equal to in our norm we must consider absolute value. Okay, the absolute value of f. I write correctly, so that this is the absolute value of this d mu x. Okay, now we can write the definition of convolution. F star g of x equal to this integral f of y g of y inverse x d mu y. Then we have the mu of x. Please note that this is the definition of convolution product. Okay, f of y multiplied by g of y inverse x. And this is less than or equal this integral f of y g of y inverse x d mu y d mu x, because we know that absolute value of any integral, for example h, okay, is less than or equal the integral of absolute value. Okay, we know this inequality in Lebesgue integral, and this is equal to by the Frobenius theorem f of y g of y inverse x d mu x d mu y. Okay, we can interchange these two integrals, and so that we can exit this real numbers absolute value f of y. Okay, then the integral of g y inverse x d mu x, and then d mu of y. But since we consider regular Borel measure, we consider x equal to g, we must add it, and we must add it this for measure, and mu be a hard measure or hard measure on G. We know that any locally compact group have a hard measure that is left invariant. Okay? Mu of y inverse A, for example, equal to mu of A, or equivalently the integral of hyx d mu x equal to the integral of h of x d mu x. Okay, h of x d mu x. You can omit this y. This measure is left invariant. Okay, so that is equal to the integral of f of y, then the integral of g of x d mu x, and then d mu y. Now you can this equal to this, because this mu consider left invariant. Okay, you must remove this or move these real numbers from the integral, and so we have this equality. This is equal to the integral of this integral multiplied by the integral of this integral. Okay, and the first one is the norm 1 of f, and second is the norm 1 of g, so that we have this inequality for or group with a hard measure. Okay, please note that. As a remark, any locally compact group G have a hard measure. Okay, okay, so that we see So for any locally compact group G, or we can write if G is a locally compact group and mu be a Haar measure on G, then L1 of G and known 1 is a Banach algebra. Okay, is a Banach algebra. And this is an algebra norm on L1, and also this is a complete norm on L1, so that this is a Banach algebra. This is an important example that we can consider, and after this we can consider this example. If we consider a weight function, example, if we consider G equal to Z, okay, and mu equal to the counting measure on G, on Z, you can following this measure on Z, counting measure, okay, then for any f in L1 of Z, let me write by this method. If f belongs to L1, f is a function from Z to C, so that we can consider, because this is countable, okay, f equal to a sequence, f equal to a sequence such as this, okay, and for any f in L1 of Z, then norm 1 of f equal to this summation, f of n equal to minus infinity to plus infinity, and by this notation this is equal to this summation, okay. Or we can consider from 0 or 1, okay. So that by this function rules, if we denote L1 of Z by L1 mu equal to counting measure. So that we have this Banach algebra. So we have L1 by this norm. Is a Banach algebra. And if we consider a norm or weights function, a function such as omega from Z plus to R plus with these two properties, omega of 0 equal to 1 and this equality, we can consider L1 of omega the set of all sequence such that this summation is finite, okay, because we know that f belong to L1, this must be finite, okay, this must be finite. In the weighted case, we consider the set of all sequence such that this summation be finite. This is the Banach function space 2. And as in another particular case, L1 of G. L1 of G is another example. This is another example. Let me write. Let G be a group. And mu be the counting measure on G. L1 of G equal to the set of all f from G to C such that this summation be finite. F of x, x belong to G. We denoted L1 of G with L1 of G, okay? So by the previous example, we have these Banach algebras to L1 of G, and norm 1 is a Banach algebra again. Banach algebra. Okay. And this is the particular case of convolution product. Okay. So by this main example, we can conclude several examples that we see in our book. L1 of G, L1 and other examples. Okay. For this example as a corollary of our general example, if we consider example let G equal to real numbers with ordinary addition as operation. Okay. Then for any f and g in L1 of R, we can consider f star of g for any x equal to the integral on R. Okay, f of y, g of y inverse equal to -1. Okay, d mu y, because our operation is plus and the inverse of y equal to -y by this operation. And this is equal to the integral of, if we consider for example -y, let me write another by another color. If we consider -y plus x equal to s, for example, okay, we consider this equal to s, then y equal to x minus s, this way, so that this is equal to f of x minus s, then g of s, d mu of s. So you can see this definition for convolution product. This is the same convolution product. So that L1 of R with this multiplication and L1 norm is the Banach algebra again. All of these examples are corollaries of our main example that we see and write in this line. L1 of T with convolution, and this norm is a Banach algebra with convolution product. Okay, with the convolution product. Okay, dear students, I think it is enough for this session. Do you have any questions? For the time or of our classes, please note that okay.
ننظم خلال شهر رمضان المبارك فصول يوم الثلاثاء على النحو التالي.
Okay. This is our first class and two and two the operator theory from you see 60, okay, from 70 to 'okay?
ننظم خلال شهر رمضان المبارك فصول يوم الثلاثاء على النحو التالي: 1. التحليل التوافقي من الساعة 33 إلى الساعة 44 2. نظرية العوامل من 15 إلى 16
It was still from. Okay, do you understand? Okay, so that tomorrow we have class at 3:30, okay?
حتى غدا فئة التحليل التوافقي من سيتم تشكيلها في الساعة 33.
Okay, thank you very much. Thank you for your attention and goodbye for now. Thank you very much.